As I mentioned previously, integrals can get quite complicated quite easily, and really without even looking too complicated. I mean, even just multiplying sometimes is enough of a complication to complicate the integral. So there's various techniques that we can use to integrate. The one other technique we get to talk about in this course is the integration by substitution. Now, before talking about that though, let me review here differentials. Remember we talked about differentials, that's been a day or two ago, but about a week or two ago. But the differentials, dy and dx. dy usually is defined in terms of dx, and it's fairly straightforward definition, but we talked about what it means graphically, but we are going to use this formula, if you will, again here. dy is equal to derivative, if you're talking about y equals, this is for y equals f of x. If the form that we'll use is actually our dependent variable is not going to be y, it's going to actually be u. But so if u is equal to some function of x or some function of some other variable, whatever it is, then du is equal to the derivative of f times dx. And it doesn't matter what that particular function is called, but anyway, remember that it's just for du or dy, it's just the derivative of this times dx. Okay, and so that'll play a role when we're talking about substitution. Just wanted to remind you of that formula, but it's not a complicated formula. It actually kind of comes out from the derivative. But anyway, remember that, recall that. All right, so where might we use this, what's called the integration by substitution? I sometimes refer to it as U-Substitution. Like substitution, I guess it's fine, but U-Substitution, also known as what I would call it. But it's useful. Take a look at this one. So you have the integral of 4x times x squared plus 5 to the 50th power dx. Okay, so we've talked about maybe sort of something like this. The complication here is that it's to the 50th power. If it was a squared, maybe 4x, x squared plus 5 squared, maybe cubed. One way we could do this is just multiply it out. But that being a 50th power, that's probably not the feasible way to go here, because that would take a while, and it would be a mile wide when we got done. So multiplying all this out just doesn't make sense, and actually there's a whole lot easier way. It's called this U-Substitution, or integration by substitution. Here's how this works. What I do is I kind of rename part of this in terms of a variable we usually call u. And in this case, in a lot of cases, what will work out to be is what's in the parentheses. A lot of times that's what you're going to assign the variable u to be. And so in this case, I'm going to let u equal x squared plus 5, and we're going to rewrite the integral with that. But not only that, I am going to use this formula because now I have u as a function of x, and so what I also want to do is I want to replace the dx with what it is in terms of du, and so to get du, we use this formula. du is just going to be my derivative here so in this case, du is just the derivative of that. That's, call it f or whatever you want to call it. We just do the derivative of that, which the derivative of that's just 2x, and it's times dx. So du is 2x times dx. Now, the goal is, when we do this U-substitution, is I want to change everything in my integral over into, instead of in terms of x's, make it in terms of u's. Well, here's the process. There's different ways you can think of it, but here's the process I go through. This is what I substituted u for, right? Or what I'm going to call u. And so I didn't really do anything with that, so let's just leave that for a moment as 4x. It's actually going to work out nicely here in just a second. This is what I called u, so instead of x squared plus 5 to the 50th, that's going to be u to the 50th. And then the other way I like to do this is I also need to replace dx by what it is in terms of du. So let me solve this second equation. Let me go ahead and take one more step here. And let's divide off that 2x. And so that gives me du over 2x is dx. And so that's what I replace my dx by, du over 2x. Okay? So I just call that u, call that du over 2x. Left the 4x for the time being. Now, what happens here is, yeah, that 4x being there actually works out pretty nicely because, look at that, that's going to cancel out. The x's are going to cancel out, and I can cancel the 4 and the 2, a little bit of 2. The 2 will go into the 4. And so, yeah, I've accomplished, that's the goal of this U-substitution, is I want to have, now, instead of x's integral, I've got a u integral. Now, you notice something about that integral. Well, that's a much nicer integral than what we started out with, because I didn't mention it, but I've got a product of variable x's in both parts of the product there. And so, as we know, we can't do the antiderivative of that. However, now, that's just a number times the variable to the power. That's just antiderivative power rule, right? This integral is much nicer than what we started with, for obvious reasons. I can just do the antiderivative power rule, can't I? Add 1, that'll be u to the 51, and so I divide the 2 by the 51. And since it's indefinite, add the plus c here. Which is a pretty good answer, but since we started out at x, let's go ahead and go back to x's. So now we just resubstitute what u is in terms of x. U is x squared plus 5, so let's put that back in here. So it'll be x squared plus 5 to the 51 plus c. Ta-da! We've integrated that particular integral. Okay? So that's the process. Let's do a couple more because, yeah, there's some things that can happen, of course, as you probably guess. Complications do occur here. That's the basic process. Okay? All right. So here's another. The integral of the cube root of 8t minus 3 dt. Okay, so this one is maybe not as complicated looking as the first one, but it's complicated enough that I'm going to have to do a little something more here, because the really the complication is, one thing I can do here is write that as the integral of 8t minus 3 to the 1/3 power dt. And so the complication comes in here, it's what I've got inside the parentheses, right? If it was just t to the 1/3, that's the power rule, but it's not. It's 8t minus 3 to the 1/3. And so the workaround is do this U substitution, and like we said, a lot of times the U that what we call U is what's in the parentheses here. So yeah, let's let U equal 8t minus 3. We also need to go ahead and get du. Du would be equal to, it's just the derivative of this, which would be 8 times the dt by that differential definition. And again, what I'm going to do is substitute at minus 3 as u, so it'll be u to the 1/3. But then I also want to substitute dt, and so my thoughts are, let's just go ahead and solve for dt here, divide both sides by 8. So du over 8 is dt. So now we're in business. There's no cancellation here, but it's just 1/8 times u to the 1/3 du, which now we can apply the derivative, antiderivative power rule on that, since this is just u to the 1/3. It's not any more complicated than just the variable. With me there? So I've got 1/8. Antiderivative power rule says that would be u. Add 1 to the, get the new power. 1/3 plus 1, 4/3. 1 is 3/3, so 1/3 plus 4/3. And just have to do the reciprocal of that in the front as well. And then plus c to that. What was that, 3/32. And then the other thing is just go ahead and go back to the original variable, 8t. U is 8t minus 3, so this would be 8t minus 3 to the 4/3 plus c. How's that? Is that okay? Question? Sir? All right. Now, how about, let's do a couple of trig ones here. So the integral of x squared times sine of x cubed plus 4 dx. Put that over so I can some room there. X squared times sine of x squared cubed plus 4 dx. Yeah, so this one's pretty well tailor-made for U substitution. The U that we substitute for, again, that parentheses involved usually helps you determine what U is. So U is x cubed plus 4 here, which would make du, then the derivative of that, which would be 3x squared plus 4 derivative of 0 dx. And since I'm wanting to substitute for dx, go ahead and divide off the 3x squared here. And that'll be what I replace dx by. Okay? All right. So now, gone back to, we have that x squared, and it wasn't what I substituted the u for here, so I'm just going to leave that there for a second. Then that's what I assigned u to be, so that'd be now times sine of u. And then dx, well, that's what I solved for here, du over 3x squared. dx is, okay? To make those substitutions. Now, again, this works out very nicely, even though I still have the x's in here, because, hey, look at that, the x squareds, those do cancel. And that's what you want if you've got those extra x's, is you want those x's to cancel. And we'll talk about some things that can happen, workarounds, but that's what we want. That's, like I said, this one was tailor-made for U-substitution. Now the integral is just 1/3, because the 3 doesn't cancel with anything. It's just 1/3 sine of u du. And again, I've gone from this, which has multiplication in it, which is bad for integrals, so to speak, to now I don't have that problem, because now it's just 1/3 times sine of u. There's not a two variables multiplied together there. So that's just antiderivative power, which is what? Negative, the antiderivative sine of u is negative cosine u, so it'd be negative 1/3 cosine u plus c. And change that back to x cubed plus 4. U is x cubed plus 4. Plus. So yeah, those with the trig integral, trig functions, pretty obvious there. What about this one? What about the integral of cosine of x times sine cubed x dx? What about that one? Well, let me just say here that since I don't have the parentheses, that doesn't, I guess, just jump out at me. But remember, and we talked about this, I think it was with the chain rule. If you got that sine cubed x, that's a nice way to write it. However, for calculus purposes, I guess you might say, it's oftentimes better to write it with parentheses. If I wrote sine cubed x in parentheses, it would be with parentheses. Wouldn't it be this? Sine of x to the third power. That's really what that means. And I need to take sine of x to the third power. Okay, so you see what I'm saying? That then helps me, because our little rule of thumb is what's in the parentheses is usually what you want to call u, right? So guess what u is here? Sine of x. And that would make du then the derivative of that, which is cosine of x dx times dx. And then if I divide by cosine of x there, du over cosine of x is what dx equals. And make those substitutions. So u is sine of x, so that would be u cubed, and dx is du over cosine of x. And so we're in good shape, because again, we like for this cancel out like that. It does once again. So that's just u cubed du. So our antiderivative involves nothing of the trig function. It's just power rule. It's 1/4 then u to the 4th plus c. Now when we go back to change that over, u is sine of x, so this is 1/4 sine of x to the 4th plus c, which, the normal way they write that is sine of x to the 4th is sine 4x, something like that. Anyway, how's that? Look okay? So yeah, if you've got, to do U-substitution, if you can write it in parentheses, that does happen. And the other one I would say, something like this, could be, whoops. Could be as simple as this, but say we've got the integral of cosine 5 theta d theta. Again, no parentheses, however, there's kind of implied parentheses there. And if we put those parentheses around the 5 theta, that's, meaning the cosine is of 5 theta, then hopefully there, obviously, yeah, the U, this is a U substitution because U would be the 5 theta, and du would be the derivative of that, which would be 5 times d theta. And so, divide by 5, du over 5 is my d theta. It's a little simple substitution, but nonetheless it is a U substitution there. So you got the cosine of U, and then d theta is du over 5. So it's just 1/5 times the antiderivative cosine, which is sine of u plus c, and then change that back to u is 5 theta. So sometimes they're fairly easy ones, but you do have to use substitution on those. Any thoughts or concerns? Look okay?